Okay, let's jump into the material then. And we're going to solve a problem that's a little long, but that's okay. Let's go ahead and set it up. So we have a Rankine cycle with a closed feed water heater and an open feed water heater. And we have the working fluid is water. And then we have 3 turbine stages. So here's a turbine stage 1. There's a turbine stage 2 and turbine stage 3. And then we have a device, it's a closed feed water heater and an open feed water heater. The other device that we need is a steam generator. And we also need a condenser. True? And we'll have some pumps. But let's get the flow through this. So it says superheated steam enters the turbine. And so we're going to come in to the turbine right here. And that'll be state 1. And it'll be 16 megapascal and 560 degrees C. So very high pressure, high temperature steam. And the condenser pressure way over here after the 3rd turbine stage is going to be at a pressure of 8 kilopascal. The mass flow rate of steam entering the 1st turbine stage is 120 kilograms per second. So m dot out of the steam generator that goes into the 1st turbine stage is 120 kilograms per second. Now, there's not 120 kilograms per second going into the condenser. Why? Because some of that steam after the 1st turbine stage is diverted to the feed water heater, the closed. And then after the 2nd turbine stage, some more is diverted to the open feed water heater. Let's continue to read the problem. The closed feed water heater uses extracted steam at 4 megapascal. So this goes from 16 to 4 megapascal. That pressure right here is 4 MPa. The open feed water heater uses steam extracted at 0.3 megapascal. 0.3 MPa. Sorry it's a little cluttered, but that's sometimes what we have to do is tuck it all in. Okay. Saturated liquid condensate drains from the closed feed water heater at 4 MPa. So that's coming out this way. Saturated liquid. And then, and the temperature equal to the saturation temperature at 4 MPa. Well, that's kind of redundant. If it's saturated liquid at that pressure, its temperature is the saturation temperature at that pressure. Saturated liquid leaves the open heater at 0.3 MPa. So let me move this saturated liquid over here. Sat liquid. So it comes out of the open feed water heater, also saturated liquid. And then it probably goes into a pump and then up that way to the closed feed water heater. Okay, this pressure is 0.3 MPa. When you have an open feed water heater, the pressure coming into it as well as the pressure going out of it is the same. In reality, anytime you have fluid flow, you have pressure drop in the direction of fluid flow unless you're converting kinetic energy into the head. Okay, in fluids, you learn that as well. Here, it's called a diffuser. A diffuser, you can do that, increase the pressure. But just think about pipe flow. Pipe flow, you just go in the direction of decreasing pressure. Saturated liquid leaves the open heater at 0.3. The feed water leaves the closed feed water heater at 16 megapascal. It's very high pressure. Then it goes into the steam generator. That's on the, what I'll call the tube side of the closed feed water heater. All right. Well, this pump boosts it from 0.3 to 16 megapascal. And then there's got to be another pump that boosts it like that. So that boosts it from 8 kilopascal up to 0.3 megapascal. All right. There's a steam trap. Where is it described in this problem statement? Drains and temperature. The saturated liquid leaves the open heater 0.3. Feed water. Well, anyway, there's has to be something done with this steam. We've put it through a trap, steam trap, and we also dump it into the open feed water heater. So for that open feed water heater, there's 3 inputs and only 1 output. Okay, let's put some state numbers. State 1, state 2, state 3, state 4, state 5, state 6, state 7, state 8, state 9, state 10, state 11. So there seems to be 11 unique states for this problem that we could talk about, right? So you want to be able to walk through and identify the pressure at each of these states. At this point, we should be able to do that. So the pressure at 1, let me kind of draw it right up here. P1 is equal to P9 is equal to any other pressures that are the high pressure of 16 megapascal. It's also P8. That's all 16 megapascal. The other pressure is 4 megapascals. So P2 is equal to 4 megapascal. Is anybody else equal to 4 megapascal? P10. That's all 4 megapascal. Now the other one is 0.3 megapascal. Okay, so what's pressure at 3 is 0.3 megapascal. True? What other pressures? P11, P7, P6, 0.3 MPa. True? And then the last one at
How is 11?
Yeah, that's into the open feed water heater. Anything coming in has to come into the same. So there's a pressure drop across that steam trap. Steam traps are like a throttling device. They just let only condensate go through, and there's a pressure drop across it. Okay? And then the last is P4 is equal to P5 is equal to 8 kPa. True? Got the pressures down. The next thing you can do is you can think of mass flow rates. All right? We're going to have a divert Y. Y is a symbol. It's a fraction. It's a fraction of the steam that comes out of the first turbine stage that goes down to feed the closed feed water heater. True? What do we want to use here? Y? No, we can't use Y. Either you go Y, W, X, something like that, but that's probably not good. So let's put Y prime because that's what the book uses. Y and Y prime, and then Y double prime, and Y triple prime if you need more of them, okay? So, and now what we want to do is we want to talk about what goes on here. You have 100% here. That's our typical notation. And then you have 1 minus Y continuing on that way. Now, what we're going to do is we're going to put this, what continues onto the condenser, 1 minus Y prime. It really helps define or clarify what do we mean by this Y and Y prime. Y was the mass flow rate that went down to the closed feed water heater divided by the mass flow rate out of the steam generator. True? What is Y prime? You have 2 choices of Y prime. It's definitely the numerator that goes down to the open feed water heater. That's not the question. But is it the mass flow rate that comes out of the second turbine stage, or is it the mass flow rate that comes out of the steam generator?
Second turbine stage.
You could work it with the second turbine stage, but the way we've written it, it's especially with the 1 minus y prime coming out of the third turbine stage, it's this definition. M dot steam generator. Okay? Okay, let's try this to see if I can show you something here. The mass flow rate that comes out of the steam generator, it either goes to divert to the closed feedwater heater, or it goes to the open feedwater heater, or it goes to the condenser. Does it go to one of those three places? If it comes out of the steam generator, it either goes to the closed or the open or the condenser. Is that true? You got to start with a truthful statement. If you don't start with a truthful statement, you'll get garbage, right? So this is, I think, truthful. Give me a thumbs up if you agree. Okay. Now, if I just divide over by m dot sg, m dot sg, m dot sg, then this is equal to 1. And I get, well, hey, that's my definition of y. You know what? This looks like a pretty good definition of y prime. That's really how we define it. It's a good definition of y prime, such that when I want to know what goes down to the condenser, based on what comes out of the steam generator, that is equal to, can you see it? I don't have room to write it. 1 minus y prime. True? So the best definition when they do it this way is it's what y prime is what comes out of the open, what diverts to the open feedwater heater divided by what came out of the steam generator. All right, little discussion there. Now, let's continue on chasing. This is 1 minus y prime. True? What comes down through here? Y. What comes over here? Y. What comes over here? Y. So in the open feedwater heater, I have y prime in, y in, and 1 minus y minus y. So what do you think comes out and goes to the pump? Is it 1? And is it 1? And is it 1? Yes, it is. So we got all our mass fractions straight. That's not trivial, but you got to do it, okay? You got the pressure straight, you got the mass fraction straight. The next thing to do is go ahead and sketch a TS diagram. I hope that you wrote down this illustration because I have to move away from it and I'm going to continue to refer back to it. We'll talk about P7 or P8 or P9 or something like that. State 11. You got to know where is that on the diagram, and I can't keep going back and forth. You'll get dizzy on me. Would you like to get a headache? You know, I'll just keep clicking back and forth. Be like a stroboscopic presentation. So here we go. Here is a temperature entropy diagram that I've really grossly exaggerated. All right. I'm going to have lines of constant pressure. What line is that? 8 kilopascal. What line is this? 0.3. What line is this? 4 megapascal. What line is this? 16. True? Something like that. So if you want, you write it up here. 16 megapascal, 4 megapascal, 0.3 megapascal, 8 kilopascal. Now, let's put on state 1, superheated way out here. All right, that's state 1. We go through the turbine. What happens to the turbine? We expand down. If it was isentropic, we would get to state 2s. If it has some inefficiency, we would get to 2 actual. In this problem, if I click back, all of the pumps in the turbines have isentropic efficiencies of 85%. All right, so we're actually going to be at 2 now. It's still superheated. What do we do at 2? We expand. That's 3s, because you're going through the second turbine stage. Maybe the expansion puts 3 actual right here. Maybe it's still in the 2-phase region. maybe 2s was two-phase high quality, but, I'm sorry, 3s was two-phase high quality, but 3 maybe superheated. You don't know. Depends how much it kicks it out. Then we expand down to 4s, but then we find you're at 4 actual. We go through the condenser. We're state 5. Is that state 5? We then go through the pump. But the pump, does it take it from 8 kilopascal, the first pump, to what pressure? What comes out of that first pump? 0.3. So it goes up to something like this. That's 6s, but you'll also have 6 actual. True? So right there is state 6. Now, that's out of the pump. That goes into the feed water heater. What else went into the feed water heater? Some diverted at state 3. True? And then also some that came after the steam trap. Okay, let's do this now. What comes, we're state 7. It comes out of that feed water heater, right? What pressure is it at? 0.3, and it's saturated liquid. There's state 7. True? Now, from state 7, you go to state 8. State 8 is compressed liquid. What pressure? 16. So you go, you skip this one, you jump way up here. That's 8s. Or you go to 8 actual in the pump. Okay. Then it comes out at state 9. Okay, where is state 9? This is where the diagram is really poor. I'm sorry about it, but state 9 is at what pressure? 16. So it's on that 16 megapascal line. But what is the temperature? The saturation temperature at 4 megapascal. So it's at this temperature, but that pressure. True? So I know I did a bad job here, but there's state 9. Sorry. Supposed to be straight across. Supposed to be straight across right here. That's the saturation temperature at 4 megapascal. Okay. When we do the numbers, you'll see between 8 and 9, there's a lot of heating of that liquid. It doesn't show it on this illustration, does it? Because those lines are so steep in that compressed liquid region, and it's hard to show them. They just all get jumbled up. Now, 9, where is state 10? Where is state 10? It's the coming out, it's the condensate coming out of the closed feed water heater, true? So what pressure is that? 4 or 0.3? 4, and it's saturated liquid. So it's right there. That's state 10. True? You see where state 10 is at? Where is state 11, my last state? It's throttled to a pressure of 0.3. Is throttling reversible? No. Is there an increase in entropy? Is S going to get kicked out to the right? Yes, it is. So don't draw it straight down from 10. Draw it kicked out to this point, 11, on that line. That's 11. So there's all of your states on a TS diagram. And you should be able to check it. Now let's solve this using Excel, okay? And in the interest of time, I'm going to try and go a little fast, but I want to cover a lot of material. So in Excel, we would start with something like the state number. And I know I have state 1, but I'm going to expand to 2s and then 2. And then 3s and then 3. Then 4s and then 4. It's just like my diagram. I had all those states on it. Now, this is always annoying when they put some to the left justify, some to the right justify. Come up here and click. They're all underneath each other. Little formatting help you, right? Then talk to me a little bit. What dictates state 1? Pressure and temperature. Make a little note over here. Pressure and temperature dictate state 1, true? How about state 2s? What fixes the state? Pressure and entropy? And then 2 versus 2s, pressure and enthalpy. Okay, let's go just do that first. Pressure in kilopascal, temperature in C. I'm going to put quality, just leave it there. Enthalpy in kilojoules per kilogram and entropy in kilojoules per kilogram Kelvin. Okay? Right. So if I put in the pressure, is that the right pressure? How about the temperature? 560? Now we use the call, start it with the equal sign. Enthalpy is a function of temperature pressure for H2O. Click on the pressure, click on the temperature, close paren, hit return. And it didn't like it because I put TP instead of PT. See, so you see what an error looks like. Didn't know what function it was. All right? Yeah, now you want to learn more about that function? Click on that little F right there, and it tells you all about it. It says you're feeding the pressure from cell C3, which has a value of 16,000, and the temperature from D3, which has a value of 560. It's returning an enthalpy of 3467.27754. I know that's a lot of digits. It's excessive. It's just numerical. And it says enthalpy in kilojoules per kilogram is a function of pressure in kilopascal and temperature in degrees C and SI units. If you want English, you have to put a little ENG right there, which we won't show you. Done. Got it? How about entropy? S is a function of pressure, temperature for H2O. Pressure, comma, temperature, close paren, return. There we go. Now we want to do isentropic expansion. So we go down to 4,000 kilopascal, true? And if I just want to bring that value down, don't retype it by hand, but say equal to, then grab that value. So the value in G4 will be the value in G3. Hit return. See how it brought it down? So that if I change this value over here, it will change the S for that line for state 1, and it will update that S below it. True? Watch. See? That's the value of the spreadsheet, 16,000. Now that these two are fixed, we want to get enthalpy as a function of pressure and entropy for H2O. Get the pressure. The enthalpy, entropy is underneath this. It's hard to do. So I click below it, grab it, and scoot it in. Or just type the cell G4. All right? You'll get frustrated sometimes. It's like, hold it. It's covering up what I want to click. Okay? So click on a side cell, grab it, and scoot it in. Okay? That's one way to do it. So there it is. Now we go to state 2. Well, what I like to do is over on the side say, what is the work that the turbine 1 does isentropically? It's ready to be calculated. It's H minus H. True? So 415 kilojoules per kilogram is the work out S, isentropic. But we have an efficiency for the turbine 1, which is 85%. So what's the work turbine 1 actual? It is only that percent of that. It's only 353 point. So if I don't want this many digits, I'll just format. There, a little easier to see, huh? Try to get the digits to line up. So now I'm ready to get state 2 fixed by knowing the pressure. Instead of retyping 4,000, why don't I just say copy that value? And then the enthalpy will be, I start from here and I take off the actual work. So that's how I have pressure and enthalpy. Now, if I want entropy, it's a function of pressure and enthalpy, H2O. And then I got pressure, comma, enthalpy. And notice this value of S. It's slightly bigger than this value. True? So it did work. It kicked it out. Now, if you want to say the quality, let's get the quality as a function of pressure and enthalpy for H2O. True? So we go pressure, comma. Enthalpy is underneath. I got to grab the edge of the box, squeeze it in, tuck it in, close parenthesis, I'm done. You'll see that it's 1. It's not 1 because it's saturated vapor. It's 1 because they're just saying it's out in the superheated region. That's this software. It's Excel. Either they're going to give you an error or they're going to give you a number back. They choose to give you a number back of 1 when it's superheated. Okay. What about the temperature? Temperature is a function of pressure and enthalpy, H2O. Let's get the pressure. Let's get the enthalpy. And there's the temperature. Now that's too many digits, but let me do this one. Temperature is a function of pressure, entropy, H2O. Here's the pressure, comma, entropy. Now, I'm going to clean this up a little bit. So look at the temperature between state 2 and 2s. Yes, it definitely is in the superheated region, and it was up higher on the diagram. If you have your diagram, you'll see, yeah, that makes sense. State 2 temperatures, what is that, 25 degrees higher than 2s. Now, we ready to go? Now, how do we determine 3s? Well, we expand it from state 2. It's the same type of expansion that we just did right here, true? If I blacken those boxes, do a Control-C. What does Control-C do? Copy. I move down and I do a paste. I really pasted the formula and now I just need to modify it. So it's not, 3 is not at 4,000. What is it? 300. And notice that it took the formula for state 3 underneath of 3s. So when I changed right here, that updated automatically. Just like if I change right here to 3,000, that updates automatic. So 4,000. See, so it copied the formula. You can take a look. The formula is the value above it. So it's relative. It's the value above. And did it copy down the enthalpy correct? Yes, it did. The only thing it didn't do was I need to do this side work over here for that second turbine stage, okay? So instead of the first turbine stage, isentropic expansion and the efficiency of the first turbine stage, I need the second turbine stage. Okay. Now, you see this is garbage because it's trying to do these two cells. Just redo the formula. So what it is you're coming in at state 2 and you're expanding to state 3s. So the work isentropic would be 541 kilojoules per kilogram. You multiply that by 85%, you get the actual work. Yeah, and you use that to update right here. So you start here and you subtract off that much. And there we go. Let me try and clean up these digits so you can see the values. So here I'm just going to copy because the third turbine stage is just like the other ones. It's not at 300, it's at 8 kilopascal. And then we need the work for the third turbine stage. It has 3 things we deal with. It's the isentropic work, it's the efficiency, and then it's the actual work. I'll have to get rid of this equation, start again, and say the isentropic work for the third stage is from 3 to 4s. And then this is the actual work, it's the correct formula there. And so the enthalpy would be from 3 subtracting the work out of the actual third turbine stage. And there you go. And so you could take a look at the qualities. Now, I can update this quality right here. Quality is a function of pressure and entropy for H2O. And then you just get the pressure over here and the entropy over here. And you can see how the qualities make sense too. And you can go back and do a lot better job of plotting that TS diagram. There. It helps show the quality. True? So if I want my notation, there's my notation, my notes to help fix it. Now, what was the next one? Wasn't it state 5? What came out We're at state 5. What's the pressure? What's the quality? It's saturated liquid, isn't it? So you just have to know how to get it. How about HL? HL for liquid. H of the saturated liquid is a function of pressure only for water. And then we'll just put in that pressure, and there you go. And then you can say equal SL. Now you notice it's starting to suggest, I can scroll down, grab one of these, and hit tab, and it finishes the equation for me. If you want to become, whatever, better at Excel. And then also T, but TL they don't put in there except for some refrigerants. So what would be another name? How about SAT? And they do. So you have to kind of know what to call it. So guess a little bit and look at your functions they give you. Or go hunting by coming up here and hitting this function, and then scroll down, and looks like, oh, right here. If you scroll down, you'll see the ones that were added in are the last ones. X-steam, psychrometrics, some refrigerants, some more refrigerants. X-steam is the one we're using because it's steam. And here's all those functions for steam. So you just have to start looking for them and guessing. Okay, is it HSAT, HL, TSAT, TL, something. Once you start to see the pattern, then you're better at guessing for this software what it is. Okay? So cancel. Let me finish this one out. TSAT, tab, at this pressure, close. So you notice that these three temperatures are the same value, aren't they? Does that make sense that they're all 41.5? On your TS diagram, they were all the same temperature. What about state? So this is a pressure and sat liquid. How about state 6? That's knowing the pressure and entropy, right? P and S. Because you're putting it, well, first of all, we're going to do 6S. 6S, isentropic compression through the pump, and then we're going to modify it to get the actual. So if it's just like before, it's just like these sequence of calculations right here. So let me just copy down the sequence, or I could repeat it, doesn't matter. Okay, let me do it this way. All right. But our pressure is not 8 kilopascal, it's back to 300. I like to use equal to so that I'll have less typing in of numeric 300. Okay, so we have the work pump 1 isentropic. What is it? It's equal to this H minus this H. True? Okay, so about 0.2, a whopping, wow, 0.2 kilojoules per kilogram. You have the efficiency of pump 1, 85%. And so the work pump 1 actual is equal to this times 85 or divided by? It needs more work, not less work, because of irreversibilities. True? So it goes up. It requires more work. So this actual enthalpy right there is this plus that. And I should clean these up a little more. Okay? That makes sense? So now this is pressure and enthalpy are dictating that state. What about this temperature? Pressure and entropy. Let me look at. Looks good. Pressure and entropy. Looks good. How come the temperature is so close? It's 41.5, 41.5. I don't know. Span it out and see if there's finally a difference. Okay, you got to go to the fourth digit. First of all, the pump didn't put much energy in. We'll see more of a significant difference. What is state 7? Pressure sat lick. Is that true? What pressure are you at? 300. True? Okay, so now we have enthalpy is equal to H liquid, the function of pressure for H2O. There's 300. And that enthalpy is a lot higher. What about the temperature? Temperature, liquid, don't like that. Sat as a function of pressure for water. There's the pressure. True? That's too many digits. There. So from state 6 to state 7, it was heated up from 41 to 133 degrees C, going through that feed water heater. Okay, how about, well, I don't need a 7S or anything like that. State 8, though, I have 8S going through the pump and 8 actual coming out of the pump, right? So we have pressure, entropy, pressure, enthalpy as my notes. It comes out at what pressure? 16, true. So it's way up there for the pressure, okay? Now, because I've done this calculation, PS and pH before, I did it right here. Let me just copy this, copy, and just do a paste. And then I'll just clean it up. The pressure, entropy, I need to get this entropy right here. Copy, paste. All right. Too many digits. Let me clean this one up. So now I need to do the second pump. So the second pump and efficiency on the second pump and the actual work of the second pump. Let's go clean up this. It's equal to going from state 7 to 8S, right? So 16.79 kilojoules per kilogram. It actually required this many, so this enthalpy is that H plus that. So we got the H there. So you can see that it's now 135.7 degrees C coming out of the pump. It came in at 133 into the pump. So there was some increase in temperature of the pump. It was a huge pressure increase. But where is state 9? Well, they tell us that it comes out at the saturation temperature for the 300, is it for 4 megapascal, right? So it's equal to T sat as a function of pressure for steam at a pressure of this 4,000, true? So I'm going to come up here and click on it if I can get this mouse to work. Please work, please. Close parenthesis there. Okay? Let me show you how much heating occurred through the closed feed water heater. That liquid in the tubes came in at 135. It went out at 250. That's a lot of heating. If you look at the sketch of the TS diagram, it showed almost no heating, but the sketch is just an illustration. It's misleading. Okay, so we know that temperature, the pressure and the temperature here for state 9, since I already calculated a lot of this, I'm just going to bring these formula down. There you go. So now I know the enthalpy and entropy. Okay. What about state 10? It was pressure and saturated liquid. True. And what was the pressure? It was coming out at 4,000. Is that true? And then I just want to copy these values because I know it's saturated liquid, and so they clean up. So it's coming out at 250 degrees C. That's the same temperature that state 9 is coming out. What about 11? It's the pressure and the enthalpy. It's through that, right. So it's equal to 300. And it's pressure, enthalpy. I can grab almost any of these. It'll work. Just come across, copy, paste. Notice, what is the quality at state 11? 25, 24%. So it's in that two-phase region, just like we said it needed to be. Okay, so I have all of the states now fully calculated. True? What I didn't do is I didn't calculate things like what y is or y prime, okay? I'll go and get now what y is. Maybe I'll leave it over here, but let's jump back to here and scroll down. If I want to know the equation for y, how do I find the equation for y? Energy balance around the closed feedwater heater. So I'm going to have what comes out of this fluid stream here, which is y times H2 minus H10, goes into this fluid stream here, which is 1 times H9 minus H8. So y, it's going to be H9 minus H8 divided by H2 minus H10. Professor, why can't we just memorize it and look at the equation sheet for it? I don't know if it's on the equation sheet. I doubt it. And you should be able to derive it quickly. But once I have the equation for y, then I can code it into Excel. The other one is, how do I get the equation for y prime? Energy balance around the open feedwater heaters. So what comes in will be y prime times H3 plus 1 minus y prime times H6 plus y times H11, and it all goes out at H7. There's one equation with the unknown y prime, assuming that you just recently finished calculating y.